what I plan to talk about mostly is these objects. These are all tables that are stored, and the schema of each of these tables is defined in the data product document. So this is a diagram showing the nightly processing. That's okay. So let's go through this part by part. So the first part is the single frame processing, where the image is acquired, crosstalk corrected. This is removal of instrumental signatures, and then you measure the PSF and background, and then combined with the calibration catalog to get calibrated exposure. The template is then acquired from acquired source. It's generated, and then the image difference is performed. So this is what the template is probably going to look like. That's the science image, and then a difference image algorithm is employed to take the difference, and you get, for a particular source that's detected, something that looks like that. The moment that happens, this is identified as a dia source. So that's the first product that we talked about. And at that point, one looks through the dia object table to find whether a source at that location or an object at that location exists or not. If it does, then this is appended as the latest part to that dia object. And if not, then this is recorded as a new dia object. So if it has previous information, then the last 12 months information that's sent out as part of the alert itself. So that's the history light curve. And if it's new, well, you start doing post photometry on that, but that arrives within 24 hours. And that's added in as a dia object. So I'm going to sort of just walk through this in terms of a light curve. So this is not a light curve of a physical object. I just picked some numbers. And the time is just serial ordering. And on the y-axis, I'm just putting down what are the signal to noise ratios that are obtained from the difference image. So what would happen in such a case is, in the first thing, it's too low, so there'd be no alert. And the same thing would be repeated because this is under 5. And on the third, you get a dia source because you've made a detection, but you don't have any history because these were never part of an object. So this is now a new dia object, and it has an alert. And then there's going to be force photometry that's going to run. And these objects would become dia force sources because you've run force photometry and you found these other measurements. And now that history is attached to this dia object. So when you get this particular object the next time, you now have this entire history added on to this. And then of course, here you're not going to get an alert. But when you find it again, you won't get anything here. But all of the other points are going to be part of the dia object history. So you'll get that, which is what is going to be transmitted as an alert. Yes.
So there's no alert for a decrease in brightness?
It's not because it's a decrease, but it's because it's below the 5 sigma threshold. Whenever it's above the 5 sigma threshold, there's going to be an alert. Okay.
But I think that's an interesting question. I mean, so there's not searches for stuff disappeared.
That'll be in the data.
Well, it is recorded.
But there's no alert.
There's no alert.
Suppose that you have a star which suddenly is not there. You don't care about it? Yeah.
Well, I mean, people could get that, but when you reprocess,
Well, it's going to be very hard for a normal person to be able to process all of
And
that.
if it never comes back, how would you know it disappeared?
well, I mean, all of this is in a database, right?
I know, but
later
back to
on,
the-
it's going to be part of the data release process where you see that you had this light curve and something went down.
Yeah, but if you have like a
orphan
failed
after
supernova,
you'll never find it.
yeah, I mean, it'd be nice to see those in low latency.
Well, I mean, I don't. Well, so the problem is detecting something at very low signal to noise is hard, right? So,
Yeah, but detecting
No.
something and then not detecting it at all is
It's
not hard.
It's not.
uh,
If you have
with a
something
huge
which is
database, it might be, but I'm not sure if.
So a
How
broker,
is it
anything
fundamentally
broker
different?
could be requested to search for this and they would find it. There's a class of stars that do this. They suddenly decrease by 8 or 10 magnitudes for a long time.
But it's the broker's functionality you're saying,
Exactly.
right? So some science community has to look for that because it's already there.
So that broker would be noticing the absence of an alert on that object in a.
Yeah.
No, but how would they?
No.
But it wouldn't be.
They will know
Well,
it doesn't work.
So like a failed super, yeah, like where it just disappears into a black hole.
So that,
Can you define what do you have in mind when you talk about broker? Is it a person that actually works on a certain data set? Or is it too many people working at night? Or how do you envision the concept of a data broker?
I was going to come to that later, but
Okay. So
briefly,
fine.
it is
If you
it is
want
an
later,
entity
Don't worry.
which, it's an external collaboration. It's not part of the project.
But is it a group or a person or many people?
Probably a group.
It would have to be many people. It's a
Yeah.
very big job.
Exactly.
It's a data center. Only
Okay.
one group has stepped forward to do this, but we're working with them all well.
Okay. Good.
But it's not
It
part
has
of.
to be funded.
Sorry.
I know.
But it's not part of LSST, right? It's an external thing.
But they operate on the raw data, the pixel data, or
They operate on the alerts.
so that's I think that's what the concern is, that the alerts wouldn't actually catch this. Therefore,
Well-
even if there's a broker for it, the broker would by definition not be able to
But
identify
the
it.
No,
alerts,
they would be able to identify if they're looking for
No, but there'd be no.
They can't look for it.
There's no
the,
stuff
the alerts have the dia object, remember?
it. The data, yeah.
yeah, but does a disappearance produce an alert?
No, but they know that you looked
No.
in this pointing.
But if it was a stable object before, there would never have been a previous
Yeah.
alert for it either, right? So it would not be a known object. It would not be represented in past alerts.
Okay, if it's a stable object throughout and it drops below 5 sigma, well, if it's a stable object, then nobody knows this, right? Because all of that
Right,
is
so then
zero,
its disappearance should be an alert.
but it's not detected.
I know, so that's important.
But it
No,
could
I
be.
mean, even we didn't detect it because it's below 5 sigma.
No, it's at 10 sigma for a year, and then suddenly it's gone.
So you're differencing, instead of having a hole, you'd have
Yeah.
a positive excess or vice versa, whatever way your difference
No, but
works.
I mean, if it is stable, then all of these alerts have been zero, right?
The problem is not the differencing, is where you put the trigger for the alert.
Yeah, so
It
alerts
has to be
are,
plus or minus, that's the whole
so
thing.
the
Oh,
idea
yeah.
is that alerts are issued on anything that moves or changes.
Yeah, okay.
Okay.
That
So
was the
it would be
misunderstanding,
minus
is that its
one.
disappearance,
Like,
does its disappearance
from
get
zero,
flagged as a
from
change?
five, yeah, okay.
So
Okay,
if
that's
it is
fine.
minus
So
5
that-
sigma, this would trigger an alert.
Okay, that was
Okay, thank
that
you.
was what we were misunderstanding.
Okay?
So when
Yeah.
we were talking about the disappearance, yeah.
Right.
Okay, good. Thank you.
Okay. So this is again part of what is going to be issued as part of alerts. There's a unique ID, timestamp, And then there is event measurements, which is essentially all of the things that you might have done on a point source. So positions, fluxes, but you also do things like shapes, which is basically moments, because you are interested in either trailed PSFs, which you would get for moving objects, as well as understanding whether it's like a dipole or not, and then fluxes and its uncertainties or covariances. There's a measure of spuriousness of the event, which is used to indicate whether this is astrophysical in nature or a result of difference imaging artifacts. There's the cutout, which is about 30 by 30 pixels of the difference image, and the template that it was subtracted from, and then the history, which is the light curve last 12 months of dia-source measurements associated with the object. And then there are characteristics of the variability of the light curve, and then there is something about the environment, which is essentially a measurement of all sources that have been found in the level 2 catalog. So that's a co-added catalog within some minimum distance of the object. So that should have things like the host. And then you'd get the IDs and distances to those objects in the yearly processes. So these details are again there in the DPDT.
So, can you characterize what the spuriousness of the event means in this case and how it's measured?
I can't tell you how it's measured, but what it's intended to do is these are measured through a difference imaging technique, and these can have false positives.
So this is just noise in the algorithm, basically? Or?
It's various artifacts that are produced in the algorithms. And there are ways in which you can go back, look at these results, and try to say, do you think that that's a real or an artifact thing? So it's that real bogus classification, more without being very specific, it's called spuriousness.
So it's something beyond the number of sigma. It's somewhat additional information besides the number.
This is absolutely additional information. In practice, probably it's going to be something like, there are surveys that have used a machine learning algorithm to do this kind of thing. It's probably going to be something similar. I don't think it's set in stone. Oh, okay. Okay, so how will these alerts be available? There'll be a hierarchy of sources. So this is the brokers that you were talking about. The example that Tony was talking about was Antares. So these are external system. They will ingest the full LSST data and stream all of this to users. There's going to be a limited LSST filtering service where science users can configure agents that return subsets of attributes, and the access will be through standard VIO clients, and they'll require authentication. And there's also a way in which historical alerts are stored in the alert database, so that can be accessed. I just want to say something. This relates a bit to the questions that you were asking. Difference imaging is the technique that has been used in optical transient surveys for a while. And what has always been seen in the large surveys is that you get a very large number of false positives. And what most of the surveys in recent times have done is, I think it was sort of introduced in PTF, IPTF, is to use some form of machine learning, mostly random forests. And when you do that, you don't have to have humans scanning this as much, but there are a large number of problems. One of them is that you still have a false negative rate. Right? So you can cut down on the false positives, say here, but that means you're missing some fraction of real objects that you wanted to detect. And so understanding that is crucial. So there's been a lot of work in trying to understand what the best algorithms is. One thing that has been fairly successful is understanding the threshold at which difference imaging must be applied. And essentially, what has happened is people have realized that it was due to correlations that what was being taken as 5 sigma was actually a different threshold, leading to many false positives simply coming from the Gaussian noise. And so now there have been alternative calculations which update these algorithms and have modified them. And the other thing, so this is the plot that I wanted to show. This is a very preliminary plot from David Rees, who's been working on this. So this has implementations of some of these algorithms where you can see that if it's noise free, then it doesn't matter as much. But if there's noise, the standard algorithm that people would use would create many more false positives here. And so they've moved on to these where the number of false positives is drastically reduced. And this is a more accurate 5 sigma threshold calculation. And the reason why we should worry about this is because this determines the efficiency with which the sources would be found. The other thing, this is also a very preliminary plot, is how this difference imaging works on different backgrounds. So if it's a galactic background, this is real data. The previous plot was just simulations. This is the kind of imaging that's going on. So there are a couple of things that I wanted to bring up. There is a program going on within LSST desk where we are trying to do image simulations of various transients, pass them through the LSST stack. And I think having electromagnetic counterparts, their light curves in that program would be very helpful in understanding what's going on. There's also a data challenge and classification being planned, and that might be another very useful thing to have light curves of electromagnetic counterparts on. So that's my summary and conclusions, and I can end here.
Any questions?
Can I ask, what are the probability that a given pixel you're going to have just completely unrelated transients going on? So you're going to see like an indoor flare, and then you'll get a supernova a year later, and they will be packaged as if they were like the same thing.
So blended.
Yeah, I don't know. I guess it's just, I don't know if you've gone through the numbers in terms of.
I don't know the numbers. The sort of cases where we do worry about this is, for example, strong lensing cases, but I don't know about other astrophysical transients where this is.
The accidental rate is really low because the resolution is less than 1 second.
Okay. So basically, a given pixel in the sky will only see one transient throughout. Okay. At most.
The brighter winds. The brighter one winds.
Well away from the galactic
Okay, so our next speaker is Rahul.